Hello Chem 152 students. For today's video lesson on this very snowy day, we are going to cover the second part of chemical kinetics, which involves instantaneous reaction rates. The first part, which we covered the last time we met, was relative reaction rates. Now, that basically looked at a chemical reaction over just in general. Instantaneous reaction rates only look at specific points in time, and the one specific point in time that we're going to find most interesting is actually at the very beginning instant a chemical reaction occurs, or in other words, at the very beginning moment that all the reactants come together. Well, for these instantaneous reaction rates problems, what we're going to be doing is actually writing what are called rate laws, which are just simply writing the word rate, which could be in concentration of molars per minute, molars per second, molars per hour, units of concentration per units of time. Now, whatever that rate equals, or whatever the value of that rate is, it will equal some rate constant K multiplied by the various concentrations of the reactants. For these instantaneous reaction rates, we do not factor in the products because this involves the reactants coming together. This is not involving the products in any way. Now, for each concentration of reactants, we're going to raise them to some exponent value. In this case, x, y, or z, or x and y if we only had two reactants, or just x, or whatever exponent value letter you want to use if we only had one reactant. Essentially, each reactant will have some exponent. It could be of a value of 0, 1, 2, 3, or upwards. Now, one thing to note, though, is that those exponents, those rate orders, they have absolutely nothing to do with the stoichiometry of the chemical reaction, whereas average, or where relative reaction rates or average rates of change of a reaction did involve the stoichiometry. These instantaneous reaction rates will not involve stoichiometry. In other words, if for reactant A, the stoichiometry is 2 and the rate order ends up being 2 as well, well, that's purely coincidental. Don't just know that the rate order exponents do not necessarily equal the stoichiometry for each of those reactants. Now, when we find the values of each reactant rate order, if we add up all those exponents together, that will give the overall rate order of the chemical reaction. And then, once we know those rate orders, each individual one, we can also solve for the reactant constant K, as long as we know what the value of a rate is for a given trial. So these instantaneous reaction rate problems, they're going to involve this following sets of data like this, where essentially you have a list of the different reactants and their concentrations at different trials. And these are the concentrations that are at the beginning of all these chemicals coming together. Now, for each trial, there's going to be a rate for that specific trial at the very beginning of all those chemicals, of all those reactants coming together. In this case, we have a reaction that has 3 different reactants. Therefore, our rate law has to take into account each of those reactants, which in this case would be carbon, hydrogen, or molecular hydrogen and molecular oxygen. And each of those are raised to some exponent. Now, here's the issue though. we don't know the rate order of each reactant. We don't know the equilibrium constants. All we have is a set of different trials with the concentration of each reactant given to us, and then the rates of each of those sets of data. Well, the nice thing is, if we were to, say, find one trial where the only thing changing is the concentration of, say, carbon, or what I should say is, if we were able to find two trials where the concentrations of all but one reactant are staying the same, then we can do what we're about to do right now, which is essentially take, say, the sets of data from one trial and divide it from all the values of another trial to basically get some things to cancel out. Now, in this case, there's a lot of unknowns, and step one, let's try to start solving for the rate orders of each particular reactant. And in this case, it doesn't matter which one you start with, but here's how we're going to start solving this particular issue. Let's start trying to figure out what the rate order for carbon, or what X equals in this particular problem set. Well, what we need to do is find two sets of data where essentially the only thing changing, or what I should say, where the concentrations of everything else is staying the same. So let's take a look at, say, trial 2 and trial 1. Well, their data says that essentially the concentration of carbon, it is only different by, in trial 1 it's 0.1 molars, and in trial 2 it's 0.3 molars. So in those two trials, the concentration of carbon changes. Now the concentrations of hydrogen stays at 0.5 molars, and oxygen, molecular oxygen, stays at 0.2 molars. So in that case, since the concentration of hydrogen and oxygen are staying the same, if we were to take the data from, say, trial 2 and divide it by the data of trial 1, all we're really doing is basically getting a few values to already cancel out. So essentially, what we're going to have in this particular case is the concentration of molecular hydrogen in trial 2 and trial 1. Since it's the same value in both of those trials, it will cancel out with itself, as well as the values of oxygen. We do not know their exponents, but essentially something divided by itself is just going to reduce to 1. So we can just ignore those. Similarly, the rate constant, which we do not know yet, that will also just divide by itself. So in the end, what we really have now is essentially this. We essentially have one rate, the value of the rate in trial 2 divided by the rate in trial 1. And that is going to equal the concentration of carbon in trial 1 raised to our rate order divided by the concentration of carbon in trial 2 raised to that same rate order. Now here's the thing, when you have two values that are both raised to the same exponent and you are basically dividing them, that can be simplified to this right here. Essentially, the concentration of carbon in trial 1 let me actually fix this. That should be trial 2 in the numerator and trial 1 in the denominator. The reason why I have the value for carbon in trial 1 in the denominator is because it is a lower value than what the value is in trial 2. Any case, the concentration of carbon in trial 2 divided by the concentration of carbon in trial 1 all raised to some exponent is going to equal whatever the value of the rate in trial 2 is divided by the rate in trial 1. So, to start essentially solving for all this, to do all this to basically solve for the value of whatever the rate order is for carbon, or whatever the value of x is, essentially, let's just plug in everything. Well, in this particular case, we have essentially the rate in trial 2 is just going to be 0.05 molars per hour. So 0.05. And we're going to divide it by the rate in trial 1, which in this case happens to also be 0.0500 molars per hour. Now the concentration of carbon in trial 2 is 0.300 molars, and the concentration of carbon in trial 1 is 0.100 molars. So effectively, what we have is this. 0.0500 divided by itself, which is just going to equal 1. And then 0.3 divided by 0.1, well, that would just be this value. 0.3 divided by 0.1, that would just be a value of 3. Now, here's the thing. Now, the way to solve for the value of x is just basically just look at it intuitively. What if we have some value of 3? What exponent can we raise it to get a value of 1? Well, that's very simple. Anything raised to a value of, say, 0, anything raised to a value of 0 would be 1. Therefore, the rate order for carbon is 0. The exponent x equals 0. In other words, its concentration, if we change carbon's concentration, it doesn't have an effect on the reaction rates. So, cool. We just solved for one of those exponents. Now, similarly, let's solve for, say, hydrogen next, where essentially we want two values where the only concentration that's changing is the concentration of hydrogen. Well, let's say we have two different numbers for hydrogen. It's either going to be 0.5 and 0.25 molars. So let's look for two trials where essentially the carbon concentration stays the same and the oxygen concentration stays the same, but only the concentration of hydrogen becomes different. Well, if we're going to look at, say, trials 2 or say trials 1 and 3. Well, in trial 1, the concentration of carbon is 0.1 molar, and for trials 1 and 3, the concentration of molecular oxygen is 0.2 molars. So effectively, taking trial 1's data and trials 3's data, I'm going to divide the data in trial 1 by the data in trial 3. Now, the reason why I'm doing 1 over 3 is because in the end, I'm going to be looking at the concentration of molecular hydrogen. In trial 1, it's 0.5. In trial 3, it's 0.25. Therefore, 0.5 is higher, so it's easier, in my mind, to keep the higher value in the numerator. So what I'm going to be doing is the concentration or the data in trial 1, and I'm going to be dividing it by the data in trial 3. And that will essentially cancel out much of these things until we essentially have the concentration of hydrogen in, say, trial 1, which we will divide by the concentration of hydrogen in trial 3. And that will just look like this. That will just end up looking like this. The rate of trial 1 is 0.0500 molars, and the rate in trial 3 is 0.0125 molars. And the concentration of hydrogen in trial 1 is 0.500 molars, and the concentration in trial 3 for molecular hydrogen is 0.250 molars. Now, effectively, what that ends up giving us is 0.05 divided by 0.0125 equals 0.5 over 0.25 raised to y. Alright, sorry for all these. .05 divided by 0.0125. That would give us a value of 4. And now 0.5 divided by 0.25, that would just be a value of 2. Therefore, what we have is essentially the ratio of our two rates equals the ratio of our two concentrations of molecular hydrogen raised to our rate order y, which ends up giving us an equation of 4 equals 2 raised to some exponent. Well, in this case, 2 raised to what power equals 4? Well, 2 raised to the second power. Therefore, our rate order for our molecular hydrogen component is going to be 2. Molecular hydrogen is second order for this chemical reaction. So, all right, we have the values of x and we have the values of y. So that's good so far. That means that the last thing that we have to really solve for, as far as the individual reaction rate orders, is going to be the rate order for molecular oxygen. Well, similarly, we just need to find two different trials where the only concentration that's changing is the concentration of molecular oxygen, while keeping carbon and hydrogen the exact same value in both. Well, in this case, what we have is, let's see, the only two distinct values in this case for molecular oxygen is going to be 0.2 and 0.1. So we need to find two trials where essentially the concentration of molecular hydrogen and molecular carbon stays the same. Well, we're basically going to need to find a trial, another trial where carbon is at 0.3 molars and molecular hydrogen is at 0.5 molars. And that would be trials 2 and 4. Now, for trial 2, the concentration of molecular oxygen is higher, so I'm going to take the data in trial 2 and divide it by the data in trial 4, just to keep the concentration of oxygen that's higher in the numerator. So effectively, all this is going to look like this. We're going to take the rate or all the data from trial 2, and we're going to divide it from the data we have in trial 4, such that it eventually cancels out everything that would stay the same and reduce to 1, and just leave us the concentration in trial 2 for molecular oxygen divided by the concentration in trial 4 for molecular oxygen. And that is essentially going to look like this. For the rate in trial 2 comes out to be 0.0500 molars per hour, and the rate in trial 4 ends up being 0.0250 molars per hour. The concentration of molecular oxygen in trial 2 is 0.200 molars, and in trial 4 it is 0.100 molars. And that quantity will be raised to whatever the value of Z is. So, okay. Effectively what we have is 0.0500 divided by 0.025. That would just end up being a value of 2. Now, 0.0 or 0.2 divided by 0.1, or 2 divided by 1, that would just be 2 as well. Now, we have the situation where we have some value equals itself raised to some exponent. Well, that basically means that in order for 2 raised to some exponent to equal itself, well, that exponent has to be 1, because anything raised to 1 just equals itself. So now we have the rate order for the concentration component of molecular oxygen. Now, since the reactant rate order for oxygen is 1, the rate is first order with respect to the concentration of oxygen. Now, here's basically some information that we can solve, knowing that we have all 3 of those reaction rate orders. Well, what are the rate orders of each reactant? Well, for carbon, we had the value of X, which we found that to equal 0. So essentially we can say, well, that is 0. For molecular hydrogen, we found that the rate order for that particular reaction was a value of 2. So essentially, for doing the same thing for oxygen, we found the rate order for that particular reactant to equal 1. Now, if you're asked for the rate orders of each particular reactant, all you need to do is just give these values. To basically write them out in words, what we could say is the reaction is 0th order when it comes to, well, no. What we're going to do now instead is, what is the overall rate order of the chemical reaction? Well, that is just simply the sum of all the exponents. If we had 2 reactants, then we would only have 2 exponents to add up together. In this case, we had a reaction with 3 different reactants, so we have 3 different rate order reactants, or reactant rate orders to add up together. So basically, what is x plus y plus z? Well, that's just going to be 0 plus 2 plus 1. That equals altogether 3. So, all right, cool. What we can say is that the overall rate order is 3. Or to put that into words, the overall rate order is 3rd order. Some overall rate orders could be, say, 0th order, 1st order, 2nd order, 3rd order. In this case, since the value comes out to 3, the overall reaction is 3rd order. Now then, if you're asked to write the expression for the rate law, here is all you need to do. Simply just plug in the values of the exponents that we didn't know back in the beginning. So essentially, to write the expression of the rate law, just write the word rate, and that equals some rate constant times the concentration of our first reactant, which in this case is carbon, raised to the 0th power. Now times by our second reactant, molecular hydrogen, raised by its rate order, which is 2, multiplied by the remaining reactant, which is molecular oxygen, and that will be raised to its power of 1. Now, this is one valid way to write the expression of the rate law. You can also write it this way, where essentially, since anything raised to the 0th power essentially drops down to just becomes 1, we can effectively say that concentration is not actually a factor in the rates. So it's perfectly acceptable to just leave anything that has a power of 0 out of the rate law expression, because its concentration doesn't have an effect on how the rate value changes. So either the first one or the second one would be a valid way to answer this question of writing the expression of the rate law, which is simply writing just rate equals some generic constant times the value of all the different times the concentrations of all the different reactants raised to their respective rate order of reaction. Now, one last thing that we can solve for when it comes to the instantaneous reaction rates is, well, the value of K. And if our rate law is basically rate equals the rate constant times our various concentrations of reactants raised to their respective rate orders, well, we can rearrange this to basically solve for K. And, well, since the concentration of carbon, any value we put in there would be raised to 0, would become 1. What we can do is just ignore it and just have the expression, the rate constant equals whatever the rate is divided by the concentration of molecular hydrogen squared multiplied by the concentration of molecular oxygen raised to the first power. For something like this, you're going to be asked to solve for the rate constant for each particular trial. Now, if we solved our exponents correctly and the data in the table we were given is accurate, the rate constant should be the same value maybe only change by a few decimal places, something insignificant, but more or less be the same value for each particular trial. So let's try and see if that is what happens. Well, let's look at, say, the value for trial 1. Looking at the rate constant in trial 1, let's just take that rate, which would be 0.0500 molars per hour. And what we're going to do is divide that by the product of molecular hydrogen, which is 0.500 molars. And we're going to square that and multiply it by the concentration of molecular oxygen, which is 0.200 molars. And, well, here's what that's going to equal. That will effectively equal 0.05. That will essentially equal 0.0500 molars per hour divided by 0.0500 molars squared. Or effectively this. Let's see. 0.050 molars per hour divided by 0.0500. And to keep all the units the same, well, that will just end up equaling a value of 1. Now, in this case, it's very important to keep track of what the actual units are as well. Well, if we started out with, say, molars per hour, effectively what we have is molars per hour in the top, and we have molars being squared in the bottom multiplied by molars again. So that is going to be molars per hour divided by molars cubed, or essentially inverse molars raised to the -2nd power multiplied by hours raised to the -1st power. When it comes to the rate constants, this you will be asked to give the units of the particular rate constant. Now, depending on the number of reactants, and also, well, what I should say is depending on the rate order of each particular reactant, the units will end up being different. So for whatever the rate constant is, the reason is it's just so that when you multiply all these different concentrations together to their respective rate orders, the rate constant should have units in such a way that they cancel out with everything else to give the rate a unit of concentration per unit time. So to write this in, essentially we have 1, a rate constant in trial 1 equaling a value of 1 that has units of inverse molars squared times inverse hours. You can also represent that as a fraction as 1 over molars squared hours squared. In other words, this is perfectly valid to do something like this. where we can either write the units of the rate constant as, say, a fraction, or just put in negative values when appropriate. Now, if we were to take the data in trial 2 to basically solve for each constant, well, let's just do it this way. Again, we don't need the concentration of carbon, so if the rate constant is just going to be the rate, let's look at trial 2's data, 0.0500, once again divided by 0.5 squared times 0.2. Well, that would end up equaling 1 again. One inverse molar squared per hour. If we were to take the data in trial 3, well, the rate would be 0.0125 molars per hour divided by 0.250 molars squared for the concentration of molecular hydrogen, multiplied by 0.2 molars for the concentration of molecular oxygen. And that would end up also equaling 1. So, all right, good so far. It looks like all these rate constants end up being the same. And just to get the rate constant for trial 4, well, that would just be 0.0250 divided by 0.5 squared times 0.1, which once again equals 1 inverse molar squared per hour. For a practice worksheet or a test, it would help to, you are welcome to write, well, you will be asked to write out each time you're solving the rate constants to basically just show that all these are canceling out appropriately. So, for example, if we were to take the value of rate constant 2, well, that would still be 0.05 molars divided by 0.5 squared over 0.2. And if we were to take the value, if we were to solve for the rate constant in trial 3, that would just look like 0.0125 divided by 0.25 squared over 0.2, or the product of 0.25 squared times 0.2, which would end up just looking like 0.0125 over 0.0125. So that is essentially all the information that we would care to solve for when it comes to instantaneous reaction rates. Not gonna lie, everyone, this was a crazy presentation to record and type. Oh my gosh. And yeah, that concludes all the information for solving these types of problems. This will show up on your tests. So before we get to the 40-minute mark, happy video lesson in instantaneous reaction rates.